In 1801, a man named Thomas Young shone light through two tiny slits in a piece of cardboard, and in doing so, he broke reality. Not broke as in, oops, we need new cardboard. I mean he cracked open the universe and found nothing, or everything, or both at the same time, which is exactly the problem. Welcome, dear viewer, to the story of how a simple experiment with light proved that you, me, your cat, and possibly your tax returns exist in multiple states simultaneously until someone looks at them. And yes, that is a scientific fact, not a philosophy degree gone wrong. The setup. Picture it. London, 1801. Napoleon is causing trouble in Europe, Jane Austen is writing novels, and Thomas Young, a polymath who spoke 13 languages, had already helped decipher the Rosetta Stone and was somehow also a physician, is bored. Newton said light is particles, corpuscles he called them, tiny billiard balls bouncing around. But I've been looking at light, and I think Isaac might have been wrong about something. And if I'm right about him being wrong, I get to be famous. So, worth a shot. Young's setup was almost insultingly simple. He took a light source, probably a candle because LEDs wouldn't be invented for another 200 years, and Young was not a time traveler, probably, and shone it at a barrier with two tiny slits cut into it. Behind that, a screen. If light is particles, like Newton said, you should see two bright stripes on the screen. Photon goes through slit A, hits the screen. Photon goes through slit B, hits the screen. Two slits, two stripes. Kindergarten math. Instead, Young saw something that made no sense. He saw stripes. Lots of them. Bright bands, dark bands, alternating like a barcode designed by a madman. What in the actual? This pattern, this interference pattern, only happens with waves. You know waves. Drop two pebbles in a pond, ripples overlap. Where peak meets peak, bigger wave. Where peak meets trough, flat water. Light was doing the same thing. But here's the kicker, and I want you to really sit with this. Light was interfering with itself. One light source, two slits, but the pattern suggested light was going through both slits at the same time, like a wave, interfering with itself, creating that barcode of brightness and darkness. Young had just proved light was a wave. The scientific community responded with a resounding, nah. See, Newton was basically the Beyoncé of physics. You don't just walk up and say Beyoncé is wrong. Newton had been dead for 75 years, but his ghost still had tenure. Young was called anti-Newtonian. His wave theory was mocked. One critic said his work was destitute of every species of merit. That's 1801 speak for, this is garbage, sir. But here's the beautiful thing about reality. It doesn't care about your feelings, or Newton's legacy, or scientific dogma. The interference pattern was real. Light behaved like a wave. Case closed. Or so they thought. The plot twist. Fast forward to 1905. Enter Albert Einstein, patent clerk, hair enthusiast, and man who would spend the next 50 years being annoyed by quantum mechanics. Einstein was looking at something called the photoelectric effect. Shining light on metal knocks electrons loose. But here's the weird part. The color of the light mattered more than the brightness. Bright red light, nothing. Dim blue light, electrons flying everywhere. This made no sense if light was a wave. Waves should add up. More brightness equals more wave equals more electrons. But that's not what happened. Einstein realized that light had to come in packets, quanta he called them, particles, photons. Light wasn't just a wave, it was also particles. And now we have a problem. Because Young proved light was a wave, Einstein proved light was a particle, and both experiments were correct. This is called wave-particle duality,
And it's not a compromise. It's not light is sometimes a wave, sometimes a particle, like a werewolf during a full moon. It's that light is both, simultaneously, always. It only shows you one face depending on how you ask the question. But wait, it gets so much worse. By the 1920s, physicists had developed technology to do something Young could only dream of. They could fire light one photon at a time, one single particle of light, through the double slits. Here's what should happen. One photon, two slits. Photon picks a slit, goes through, hits the screen. Do this 1,000 times, you get two piles of hits, one behind each slit. Particles, common sense, the universe behaving itself. Here's what actually happened. They got the interference pattern, the wave pattern, stripes, from single photons, fired one at a time. Let me say that again because it's important. One photon at a time. Each photon had no other photons to interfere with. It was alone, isolated, a hermit photon, and yet it interfered with itself. It went through both slits simultaneously, like a wave, even though it was a particle. At this point, any reasonable person would say, okay, clearly the photon splits in half, goes through both slits, and recombines. But here's the thing. Photons don't split. They're fundamental particles, indivisible. You can't have half a photon. It's like trying to have half a pregnancy. You're either pregnant or you're not. The photon is either there or it's not. So this single indivisible packet of light was somehow going through two holes at once, occupying two positions simultaneously, being in two places at the same time. If this is starting to sound like that one friend who says they'll maybe come to your party and then shows up and doesn't show up at the same time, yes, exactly. Welcome to quantum superposition. The observer effect. Now, physicists are nothing if not persistent and suspicious. They looked at this result and said, okay, photon, you want to play games? Let's play games. They added detectors to the slits, little sensors that would tell us which slit each photon went through. No more mystery, no more maybe both. We're watching now. We're observing. Surely, if we catch the photon in the act, it has to pick a side. And the photon picked a side. The interference pattern vanished. Gone. Replaced by two simple stripes, exactly what you'd expect from particles. The act of measuring which slit the photon went through forced it to behave like a particle. The wave nature disappeared the instant we looked. Let me be clear about what happened here. The photon was not secretly a particle all along. It was not hiding its wave nature. It was a wave. It was going through both slits. And then we looked, and it wasn't. The universe literally changed its behavior because we were watching. This is called the observer effect, and it is not a metaphor. It is not observation in the sense of becoming aware of something. It's physical interaction. To detect which slit the photon went through, we had to interact with it. And that interaction collapsed the wave function, collapsed all those possible states into one definite state. But here's where your brain might actually try to leave your skull. In 1978, physicist John Wheeler proposed something called the delayed choice experiment, and it is the most no that can't be right experiment in physics history. Here's the setup. Photon goes through the double slits, but after it passes through, after it's already committed to being a wave or a particle, we randomly decide whether to put up a detector or not. The choice is made after the photon has passed the slits. If the photon already went through both slits as a wave, it should create an interference pattern, right? The decision is made. The wave has passed. Too late to change now. Wrong. If we put up the detector after the photon passed, we got two stripes, particle behavior. If we didn't put up the detector, we got interference, wave behavior. The past behavior of the photon, what it did, depended on what we chose to do in the future. This is not time travel in the sci-fi sense. The photon didn't go back in time. But somehow, the universe maintained both possibilities, wave and particle, until the very last moment, until a measurement forced a decision. The past wasn't determined until the future observed it. And if you're thinking, well, maybe the photon just knew what we were going to do, congratulations, you've stumbled into another quantum nightmare called superdeterminism, where everything in the universe is
pre-planned and free will is an illusion, which is technically a possible interpretation, but it requires that the Big Bang itself encoded every measurement choice you would ever make into the initial conditions of the universe. So your options are: A, the future affects the past; B, the universe is entirely deterministic and you're not actually choosing to watch this video; or C, we don't know. We genuinely don't know. The deep dive. Let's go deeper, because we haven't even talked about the mathematics yet, and the mathematics is where this stops being weird and starts being mathematically proven to be incomprehensible. This is the Schrödinger equation, developed by Erwin Schrödinger in 1926. He later said he wished he'd never met the woman who inspired him to discover it, which tells you everything about how physicists feel about quantum mechanics. The Schrödinger equation describes how quantum systems evolve. But here's the thing, it describes them as waves, probability waves. The photon isn't at point A or point B, it's described by a wave of probability spread across both points, across all points, until measurement collapses it. This isn't we don't know where it is. This is it literally is everywhere it could be, with different probabilities simultaneously. The math insists on this. If you treat the photon as having a definite location before measurement, the math breaks. The predictions fail. Experiments don't match. So the math works. The math works beautifully. It predicts the double-slit results to incredible precision. But what the math is a wave of potential, a wave of could be. And when we measure, that wave collapses to a single point. The potential becomes actual. The many become one. But what is measurement? What causes the collapse? This is where physics becomes philosophy, where Nobel Prize winners start shouting at each other at conferences. The Copenhagen interpretation, the shut up and calculate approach, says we shouldn't ask what causes collapse. The math works. Use the math. Don't think about it too hard or you'll go mad. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave never collapses. Instead, reality splits. Every possible outcome happens in different universes. The photon went through the left slit in universe A, the right slit in universe B, and both in universe C. We just happen to experience one branch. The others are equally real, but inaccessible. This means every quantum measurement spawns new universes. Trillions upon trillions of them every second. A multiverse of incomprehensible size where every possible version of history is playing out somewhere. And if that sounds extravagant, if you're thinking that's too many universes, consider that the math for many worlds is actually simpler than Copenhagen. It removes the mysterious collapse entirely. It just says the Schrödinger equation applies to everything always, including observers. We become entangled with the quantum system, and from our perspective, it looks like collapse. But the other possibilities are still there, still real, still happening. Then there's pilot wave theory, the hidden variables idea. Particles are real. They have definite positions, but they're guided by a pilot wave that goes through both slits. The particle goes through one slit,
but the wave goes through both, and the wave guides where the particle ends up. No superposition, no collapse. Just particles and waves, separate but connected. This was actually proposed by Louis de Broglie in 1927, the same year the Solvay Conference declared Copenhagen the winner. It was ignored for decades because Bohr didn't like it. But it's mathematically valid. It makes the same predictions as standard quantum mechanics, and it preserves a single definite reality. The catch: pilot wave theory requires that particles instantaneously communicate with each other across any distance. Non-locality, Einstein's spooky action at a distance. And in 1964, physicist John Bell proved that any theory that matches quantum predictions must have this non-locality. There are no local hidden variables. Reality is either indefinite, superposition, or non-local, spooky action at a distance. Pick your poison. And we haven't even touched on quantum decoherence, the modern understanding that measurement isn't special, it's just interaction with the environment. The photon doesn't need a conscious observer. It just needs to interact with anything. Air molecules, the screen, a stray electron. The environment measures the photon constantly, collapsing superpositions, creating the classical world we see. But this just pushes the question back. Why does interaction with the environment cause collapse? Or apparent collapse? Or branching? The math doesn't say. The math just works. Richard Feynman, Nobel Prize winner, bongo player, genius, famously said, "I think I can safely say that nobody understands quantum mechanics." He wasn't being humble, he was being honest. The greatest minds of the 20th century working on this for decades, and we still don't know what's really happening when a photon goes through two slits. The implications. So why does this matter? Why should you care about photons and slits and waves that are also particles? Because this isn't just about photons. Everything is quantum. You are quantum. Your atoms are held together by quantum mechanics. The screen you're watching this video on works because of quantum tunneling in transistors. The sun shines because of quantum tunneling in fusion. The entire modern world, computers, lasers, MRI machines, GPS, depends on our understanding of quantum mechanics. But more than that, and I want you to really feel this, the double-slit experiment reveals that reality is not what it seems. The solid, definite, predictable world of your everyday experience is a kind of illusion, a collapse of infinite possibilities into single outcomes, a temporary, fragile state that exists only because of constant interaction, constant measurement by the environment. Underneath everything, the universe is a roiling sea of probability, potential, superposition, and we, conscious observers made of quantum stuff, somehow navigate this sea, collapsing waves into particles, creating the classical world through the very act of existing in it. This raises questions that physics cannot answer. What is the nature of observation? Does consciousness play a special role? When Schrödinger proposed his famous cat thought experiment, a cat in a box that is simultaneously alive and dead until observed, he meant it as a reductio absurdum, a proof that quantum mechanics must be wrong, because obviously cats can't be both alive and dead. But here's the terrifying thing. The experiment has been done, not with cats, animal ethics boards frown on that, but with molecules, buckyballs. 60 carbon atoms arranged in a soccer ball shape. In 1999, researchers sent buckyballs through a double-slit apparatus, and they got an interference pattern. The buckyballs, 60 atoms, nearly 1,000 protons and neutrons, were in superposition. They went through both slits. They interfered with themselves. In 2013, the record was extended to molecules of 810 atoms, 10,000 atomic mass units. Visible to the naked eye if you have good eyes, and they still showed quantum behavior. The boundary between quantum and classical isn't fixed. It's not about size, it's about isolation. Protect a system from environmental interaction, and it stays quantum, bigger and bigger, weirder and weirder. So where is the limit? Is there a limit? Could we, in principle, put a cat in superposition? A human? The entire universe? Some physicists think that once you factor in gravity, once an object is massive enough to curve space-time, quantum effects break down. This is the realm of quantum gravity, the holy grail of modern physics. We don't have a theory of quantum gravity yet. We don't know how to reconcile quantum mechanics with general relativity. But here's a thought that should keep you up at night. The universe, right after the Big Bang, was in a state of perfect quantum superposition, all possibilities coexisting. And then something happened. Expansion, cooling, decoherence. The universe measured itself, collapsed into definite states, and here we are. Was the early universe like a giant double-slit experiment? Are we living in one branch of a quantum wave function? Is the multiverse not just possible, but inevitable? We don't know, but the double-slit experiment, that simple 1801 demonstration with light and cardboard, opened the door to all of this. It showed us that reality is deeper, stranger, and more wonderful than our senses reveal. So here we are, over 2 centuries later, and Thomas Young's experiment still breaks physics.
Still breaks our intuitions. Still breaks any attempt to say the universe works like this, simply and clearly. Wave-particle duality, superposition, the observer effect, delayed choice, quantum decoherence, many worlds, pilot waves, the measurement problem, the limits of knowledge. The double-slit experiment isn't just a physics demonstration, it's a mirror held up to reality itself, showing us that our assumptions about how things must be are just that, assumptions. The universe is under no obligation to make sense to us, it simply is. And our job, as curious, conscious pieces of that universe, is to keep looking, keep questioning, keep shining light through the slits and seeing what pattern emerges. Because every time we look, we learn something new. Every time we think we've figured it out, the universe surprises us. And that endless mystery, that bottomless depth hiding behind the simplest questions is what makes physics the greatest story ever told. Or at least the second greatest. I like to think I'm doing okay with this one. If your brain hurts, good. That means you're thinking. Leave a comment with your favorite interpretation of quantum mechanics, Copenhagen, many worlds, pilot wave, or I need to lie down. Subscribe for more stories that break reality. And remember, the universe is stranger than we can imagine, but it's also stranger than we can imagine. And that's beautiful. Oh, and one more thing. You might be wondering, if observation collapses the wave function and the universe is full of observations, how did we ever discover wave behavior in the first place? The answer is we cheated. In the double-slit experiment, we don't observe which slit the photon goes through. We observe where it lands on the screen. The screen is the observer. But the screen doesn't tell us which slit. It just tells us the final position. So the interference pattern survives, encoded in the distribution of many photons. Each individual photon collapses at a specific point, but the pattern of many points reveals the wave that guided them. It's like if you threw 1,000 darts while blindfolded and someone else mapped where they landed, you could figure out the shape of the target you were aiming at, even though each individual dart hit one specific spot. The wave is the target, the particle is the dart, and we're all just trying to figure out where we're aiming. Or something like that. Quantum mechanics is weird,